Welcome to today's session on Introduction to Compensators, Lead Compensators in Control Systems. In this video, we will understand why compensators are needed and different types of compensators and the concept of lead compensators and their characteristics, design procedure and effects and applications. So let us begin why this topic is important. In practical control systems, engineers often face problems such as slow system response, oscillations, poor stability, and inaccurate output tracking. So these issues affect industries such as robotics, industrial automation, aerospace, and motor control applications. If these problems are not solved, they may lead to equipment damage, production loss, and safety hazards and economic losses. Therefore, improving system performance becomes extremely important in control engineering. So this is where compensators play a major role. So need for compensation means an uncompensated system usually suffers from poor transient response, inadequate stability margins, poor steady-state performance and slow system performance. To overcome these problems, compensation techniques are introduced. So the main goals of compensation are improving transient response and increasing phase margin, enhancing stability and achieving better steady-state accuracy. Among different compensators, the lead compensator is mainly used to improve transient response and system speed. So it provides a faster response, better damping ratio and improved stability. So now let's see the types of compensators. The compensators are generally classified into lead compensator, lag compensator and lag lead compensators. So in this, lead compensator provides a phase lead and improves transient response and increases bandwidth, enhances phase margin. So for lead compensator, the parameters A is greater than 1. So if we consider in lag compensator means it improves steady state accuracy, reduces steady state error and increases low frequency gain. For a lag compensator, A is less than 1. If we consider a lag lead compensator, this combines the advantages of both better transient response and improved steady-state performance. These compensators are widely used in practical control systems. So let's move on to the introduction to lead compensators. So now let us focus on the lead compensator. The definition is a lead compensator is a phase lead network that adds positive phase angle near the crossover frequency. The main purpose is to improve phase margin, increases stability and speed up system response. The transfer function of a lead compensator is Gc of S is equal to K into 1 plus A Ts divided by 1 plus Ts, where here the A greater than 1 and T is the time constant and K is the gain. The lead compensator can also be implemented using RC circuit and the important parameters are T is equal to R1C and A is equal to R1 R2 divided by R2 and K is equal to A. Because of the phase lead introduced, the system becomes faster and more stable. Characteristics of lead compensator. The lead compensator has several important characteristics, that is maximum phase lead, and this phase lead is phi m is equal to arc sine A minus 1 divided by A plus 1. This phase lead increases, the value of A increases. And frequency of maximum lead, that is omega m is equal to 1 by T root A. and the pole 0 locations are zeros. S is equal to minus 1 by AT, pole S is equal to minus 1 by T. Because the 0 is closer to the horizon than the pole positive phase, lead is produced. Overall, the lead compensator increases bandwidth, improves damping, reduces overshoot, and provides a faster transient response. The design procedure for lead compensator is that step 1 is determine the specifications, that is identify desired phase margin, settling time and steady state error requirements. And step 2 is calculate required phase lead, find the additional phase lead using the formula and determine the parameter A. And step 4 calculate the time constant, that is T. T is equal to 1 divided by omega m into root A. And then step 5 is phase compensator. Implement GC of S in a cascade with plant. And step 6 is verify the performance with all specifications met through analysis. And effect of lead compensator. So let us compare the uncompensated and compensated systems. The uncompensated system gives the low phase margin, narrow bandwidth, slow response and high overshoot. But after adding the lead compensator, it gives the phase margin improves, bandwidth increases and response becomes faster and damping improves. Thus, the lead compensator significantly enhances the system performance. This is the design example of the lead compensator. And the given system is G of S is equal to 10 divided by S into S plus 1 into S plus 2. The desired phase margin is 45 degree and steady state error is less than 0.1. And the applications of this lead compensators are, the lead compensators are widely used in many engineering systems, that is motor speed control, used in DC motor drives, servo systems and position control systems. Robotics used for robotic arm movement and precision positioning. For aerospace systems applied in flight control, autopilot systems and aircraft stability control. So industrial automation, it gives the many temperature regulation, pressure control and flow of control systems. So their ability to improve speed and stability makes them highly valuable in industry. So let's move to the conclusion and summarization part. So let us summarize today's session. We discussed about the need of compensator, types of compensators and introduction to lead compensators and their characteristics, design procedure and practical applications. The lead compensators is essential technique in modern control system design. Thank you.